So, just like before, we're going to continue on with where we left off for our chapter review, integration. And then on the Tuesdays, we'll have a look at that probability stuff that you mentioned last time. Actually, how far into probability are you at right now?
I think we've just started the basics of probability.
Yeah, to some of the fundamentals.
Sorry, no, basics of statistics.
Statistics. Okay.
Yeah,
Statistics
we've
for
already.
discrete, like mean, median. Oh, not median. It'd be mean. Geez, actually, it's been a while since I looked at it. I forget which
We
ones.
just had one class on this.
Yeah.
We've gone over the probability stuff. We started um, the
Maybe I'll pull up the chapters and
statistics.
you can have a look at that. Like so there's discrete, the sample space is conditional probability, mean variance, standard deviation, like chapter 13 stuff. Yeah.
Yeah, I think we did up to standard deviation.
Yeah. Okay. So you would
Maybe.
have basically clocked out on
Yeah, I
chapter
think we
13.
just did like. I think we did like. Wait, no, I think we're. Actually, I have no idea what we're up to.
That's fine. So if you know more about it, let me know when you by the time I get to Tuesday. We'll probably do a review of most of this stuff anyway. Maybe some of the really fundamentals we'll keep aside because some of those are really basic. But yeah, we'll start more or less where you're up to. But that'll be for Tuesday. For today, we'll be continuing here. I had a look at question 10 ahead of time. This one's kind of interesting, I found. It's one of the first times you're ever trying to find the inverse of a circular function, which isn't something that's very typical at all. But we'll get to there eventually. For now, part A is just sketch the graph. I mean, this is just a circular function, and this is tech enabled, and so not too much worth doing there as far as discussing. So the next part is more interpretation, what the integral from 0 to pi would be as far as the area. So I think what we'll do is I'll just get the graph up and then we'll observe from there. So 2 sine x, take 1, and we're doing it from, whoops, doing it from negative pi on 2 to pi on 2. Less than equal to x less than equal to pi on 2. And we get that graph. So when we're evaluating from 0 to pi on 6, the integral of that, we're obviously just finding the area underneath the curve from 0 to pi on 6. That's the gist of it. Now they chose negative pi on 2 to pi on 2 quite specifically as a domain for this, and the reason why is because that will lead into part C, finding the inverse function. Before we look at finding the inverse itself, could anyone suggest why a domain of negative pi on 2 to pi on 2 is almost required before part C can even be done? There's some conditions around the validity of inverse functions.
So when we take the inverse of it, the sign will become sine inverse, right?
Yeah, so we'll turn it into
So
some form of
it's
sine inverse.
so the values will only be valid between -1 and 1, right?
Negative 1 and 1, as in like domain wise?
Yeah.
Yeah, okay. And so what's the relevance of negative pi on 2 to pi on 2 regarding that then?
Um. Okay. So,
Bit of background. Yeah, I'll just take it from here then if you got a bit of background noise. So basically, yeah, the relevance there was, if we remember our unit circle, subbing in pi on 2 or even plus minus pi on 2 will give you the peaks and troughs of the sine graph, because pi on 2 takes you to the top of the unit circle, negative pi on 2 that takes you to the bottom of the unit circle. There's no further dilations or anything like that in our function f of x, and so that's going to get you the peaks and troughs. That's one way to think about it, right? Maximizing the full relevant range and therefore domain of the inverse function. The other explanation for this, which is more specific to inverse functions, is that an inverse function can only ever exist so long as the original function is one-to-one. So simply put, like if we had a parabola, for instance, we try to find the inverse function of that without restricting its domain, the output of that would no longer be a function, it would be a relation. You would get the graph of y squared equals x, or something like that. And that is no longer a function, as I said, it is a relation. So the reason why, or I guess another reason why negative pi on 2 to pi on 2 is a domain for this is because that is a domain such that we cause a circular function to go from many to one to now one to one. That is to say, it's basically strictly increasing or strictly decreasing for the whole duration. This one, left to right, is always increasing. As soon as it curves downwards, you now get a relation when you do your inverse. So realistically speaking, any domain between negative pi on 2 and pi on 2 could work. Furthermore, if you took different cycles, like this graph would continue on, you could take different subsections of the domain. But this is something, and even like for those who are doing Spesh, like this is something that Spesh actually teaches. The implied domain of your circular function inverses is likely to be negative pi on 2 to pi on 2, simply because that maximizes the effective domain of the inverse. So that's a bit about that I thought was interesting to share. Now when it comes to actually finding the inverse, it's not actually trickier than any other inverse. You're still following largely the same steps. However, it's not particularly common to do an inverse function for a circular function, so I could imagine that some people might find it confronting. So, with that in mind, does anyone want to take a stab at how we might find the inverse of this function? Or even perhaps remind me the steps of finding an inverse function.
Put x in the y position and y in the x position.
Yeah, that's right. Basically, every x is going to be replaced with the y, and every y is going to be replaced with the x. In this case, obviously, I've written f of x here. That is the same as y. So, what that swap would now look like would be x equals 2 sine of y minus 1. You could put f inverse here if you wanted to, but that's more writing than otherwise necessary. So long as you put f inverse at the very end once you've done all your calculations, it's fine to just use y as a variable there. But yeah, that's step 1 for all inverse functions. Just start by swapping the x and the y location.
Yeah, we take the one to the other side and the 2 as well.
Yep. Get
then the sine.
Wait, sorry, did you say bring the sine to the other side? So how do we, I think you might have cut out when you said it. How do we now follow it up from here?
We can, we take the sine to the other side.
Yeah.
The sine, it becomes sine inverse.
That's it, yeah. So kind of like how we can wrap logarithms around both sides of an equation, we can also choose to wrap the sine inverse around both sides of an equation. Sine inverse on both sides. And just worth pointing out, because composite functions is something that we should be more familiar with. Anytime you have f inverse of f of x, or even the other way around, f of f inverse, it always ends up equaling whatever was left in the brackets. So this is f of x, this is f inverse of x. As long as you have the composition of f inverse and the original, whatever's on the inside is left alone. Which is why when we wrap both sides by sine inverse, what we're left with on the left hand side is still just going to remain sine inverse of x plus 1 on 2. But what's going to simplify on the right hand side, because you have sine inverse wrapped around sine, they cancel out, leaving you with just the y, which is in the inside of the brackets, which, because we're on our last line of working, we will now label as f inverse of x, because that's what the question was asking us to solve. Not y, but f inverse. So yeah, it's not something we do explicitly a lot. We technically do this all the time when we're solving circular functions. When we're solving circular functions, but we never really use this notation quite often. So it's nice to refresh our minds on that. If there's any questions about how any of that works, let me know. Otherwise, yeah, that is what that's all about. Your CAS can even graph this as well. Like part D doesn't necessarily say to graph it, but it's still got to do with like area under curve and such, because we're doing definite integrals. So if we were to use, well, find the graph of sine inverse, it's under your trig stuff. You can see sine inverse directly under sine. So if I suss that out, sine inverse x plus 1 over 2, we should see a perfect reflection of what that would look like across the line y equals x. We can see that if I reorient the camera such like this, we get that perfect reflection across the line y equals x. We'll further note that I didn't put a domain on this function. I didn't put a domain on the inverse function. And by not putting a domain, it assumes maximal, but not necessarily just maximal domain, but the I guess the one closest to the origin. As we discussed previously, circular functions can repeat forever, and the default assumption on the CAS will be get the ones closest to the origin and maximize it, unless you say otherwise. And yeah, we can see that's what's happened. Next part was part D, so actually evaluating that integral. This being tech active, you can literally just evaluate this, right? Like we have, where is it? We have the graph f3, so all we would have to do would be get out of CAS 0 to 1, and then use exactly that function, and then we'll get the answer we're looking for. Now, it didn't necessarily say anything about decimal places, so I wonder if maybe there is no great answer for that. Let me have a quick look at the answers to make sure there's no exact for it. No, there isn't exact. That's a bit interesting. Okay, so it looks like the CAS has a bit of trouble getting exact values for this sine inverse graph. So let's think about a different way by which we can get an exact value. Because decimal isn't going to cut it here. It didn't say anything about a number of decimal places. I'll transfer over to the graph that we have here. We're trying to go from 0 to 1 of f inverse. Graphically speaking, we need to find another way of doing this rather than just going straight to the definite integral. Just to make it a bit clearer, maybe what I'll do is I'll put in some vertical lines. So we want to do between 0 and 1 on the black graph. So just this little section in here. Maybe I'll fix this domain up a little bit. We'll go, yeah, we'll do plus minus pi on 2. Negative pi on 2, pi on 2. Maybe a bit more on the y-axis. Go negative 3 to 3. That's a bit better. Okay. So basically, the right hand side of our y-axis up until the end point of the black line. We want to find that area under the curve. But what we figured out was just doing a definite integral on that didn't really work out too well, at least as far as the CAS goes. We didn't get our exact value. So we did an alternative approach to getting there. How might we get there? One thing I'd be tracking would be the relationship between f of x and f inverse. They are reflections of each other across the line y equals x. So if we can't use f inverse, maybe there's a funky little way we can use the original function to get an equivalent area. So when we're talking about using the inverse function or the original function and how they have equivalent areas, we can simplify things down into saying that effectively the x and y are swapping positions when it comes to inverse functions, right? So an equivalent area from 0 to 1 on the x for the inverse function, which is what we're trying to find, would be the same as finding whatever the equivalent is for 0 to 1 on the y. Right, because 0 to 1 across the x flips to 0 to 1 along the y for the inverse pair. That's one other tip we could follow. But integrals don't necessarily use y values on their terminals. They use x values. So if we know the equivalent for the original would be 0 to 1 on the y rather than 0 to 1 on the x, we need to somehow roll that back into x values. How might we do that? So basically, any function is just a relationship between x and y. Alright, you have function of x equals y. So long as you have the y values or the x values, you can then find the other thing. Now this might take different levels of complexity depending on how hard the function is, but when you go to CAS, you don't have to worry too hard. So if we know the equivalent is 0 to 1 on the y for the original function, what we're going to do is take that original function and then solve for the equivalent x values. So basically, actually I've got to figure out which one that was. Our original function was called f2, and we got that domain already, which is good. So we'll solve for where f2 is equal to 0. We'll solve for where f2 is equal to 1. That gives you the x pairing that exists for those y coordinates. Now that we've made that mapping, we're now able to solve things purely in terms of the function that we started with rather than the inverse, which was playing a bit strangely with us. So if we have a look at what we have achieved, I think maybe Do we need this one still? We kind of do. Probably don't need the x equals 0. Yeah, okay. What? I'll just put in the values we just found there. So we had x was pi on 6, and we had pi on 2. So the x equals pi on 2 one is all the way out here. X equals pi on 6 is this. So what that has done is found this equivalent area in here. And it's saying that's equivalent to doing this. That's the gist of it, really. Flipping the x-related information on the inverse to y-related information on the original. But then, because we're trying to evaluate an integral, we need to get that y-related information back into x information, specifically for the f of x function. So we take that y information and then solve it accordingly. So we'll do exactly that. Pi on 6 to pi on 2. f2 of x, because that's the original function. Oops. And we get our exact. Any questions there? Definitely a tricky one. Especially with like the circular functions, because it's kind of hard to picture them visually like I would like to. I found like it's something we use a lot with logarithms and exponentials, tech-free, because you can't, hang on, which one can't you anti-diff? Yeah, because the diff of log goes to 1 on x, but you can't do the anti-diff of log. And so sometimes the question will ask you to find the anti-diff of log, but you can't do it. So you got to use the inverse of that, and then find the equivalent area that way instead. So when we were doing logarithms and exponentials, we did a lot of this. This is just applying the same sort of thing to functions that are a bit sketchier to look at. Right, like it's not particularly great to look at sine inverse when it kind of just shoots off and then disappears on the edges. It's a bit harder to conceptualize the equivalent areas. But it's the same sort of idea as that. Anyway, if there's no further questions, we'll move on. Question 11. Okay, what have we got going on here? Attempting to draw a quarter circle, radius 10. What do you get? A exponential kind of equation, whereas the quarter circle should have the square root kind of equation. First question, find dy dx for both functions. This is obviously trivial. Dy dx just means finding the derivative, and the CAS can do that for us immediately. This being tech active, we're not going to bother with the whole product rule and chain rule that would be necessary to do it tech-free. So I think what I'll do is I'll just clear the workspace. So we can start with fresh variables. Function is equal to, let's do the exponential first, e to the x over 10 times 10 take x, and then, oops, missed that. We'll go I of x for the next one, and that will be the root, square root 100 take x squared. Diffing both of these, obviously, just use the derivative equation, and then write down exactly what you get. Yeah. That'll be the derivative of the exponential one, this will be the derivative of the square root thing. Nice and easy. Part B, find the gradient of each of those functions when x equals 0. Gradient, derivative, these are things that are quite related to each other. Anyone want to refresh my memory on how we can use derivative to find gradient at a point? That's fine, no worries. It is a fairly basic topic. You are simply just shoving in the x value into the derivative. Derivative itself is a function that explains the gradient of the original function for any value of x. So when it says find the gradient of the functions when x equals 0, one of the things you would do would be find the derivative of that function and then set x equal to whatever the x coordinate is, which in this case is 0. You can do that in a bit of a funky way with the CAS by using the sort of domain operator that you usually use for setting domains. You can actually do that to set your x value off rip like that. The reason you do it that way rather than subbing it in directly, now in this case it's actually going to come out to be the same thing, so maybe the maybe the I of x one will be a bit different. Please tell me it is. Really? They come out to be the same thing. Point being, the difference between these two things, one has you subbing in the value first and then find the derivative of that. Problem is, if you find h of 0, or whatever it is, it's going to be some constant value. And the derivative of any constant is always going to be 0. This has just been a bit of a coincidence that the gradient at each of these points has been 0 anyway. So in this case, you don't get punished if you do it the wrong way around. But yeah, just noting the difference there. So you can do that in one line succinctly like that, or alternatively you could just define the derivative as its own separate function and then shove in to that respectively. Part C is the exact same question, but now x equals 10, so sure, why not? It's for the original function here. Actually, maybe here's a way that we can, well, first let's test. There we go. Okay, that one gives us negative e, and if I tried it the other way around, we're still going to get 0. There we go. That's showcasing the difference there. You need this syntax for doing what we're trying to do here. Doing it this way results in a bad result, always 0. So, answer to part, what was it, C there? That's just going to be negative e. If you want to, you can validate these on the graph itself. So if we take a look back at the screen share, the graph of the e to the x thing, that's the blue dotted line. For x equals 10, if we look at what the gradient would be at that spot, the graph is trending downwards, and so we would expect it to be a negative value. So the fact that it's negative e seems plausible. Part D. Finally got to start thinking a bit more. Find the area of the shaded region, and now we're getting it to 2 decimal places. So this time we don't have to worry too much about exact values at all. Area of the shaded region, that's going to be the area bound between the red curve and the blue curve. How do we find areas of shaded regions? Can anyone refresh my memory on that?
In the area between two curves.
Yep, area between two curves. What's involved in that?
The integral of the top curve minus the bottom curve.
That's exactly it. So the top one will be the red one, which is the square root. It's physically above the blue one. So I defined the red one second, so that's going to be our I of x. And that will be our top take our bottom. And all we're going to do is set the integral terminals, which will be what is effectively the domain. So how far horizontally does our area spread? If you're just looking at the graph here, it can be a bit what's the word? You can be a bit led astray to think maybe it's not quite going to start at the origin. Maybe it starts somewhere earlier, just based on what they've drawn on the axis. So if you wanted to validate that further to make sure that it doesn't start at the origin and it does maybe start later on, one thing you could do is just solve where these functions intersect. So we'll just put in at least a placeholder 0 to 10. and before taking that as our final result, we'll just make sure that they do in fact intersect at those spots. Because just based on the picture they had there, it looks like it intersects a bit further from the origin. I'm fairly certain it won't though. I of x equals h of x, comma x, 0 and 10, which is what we expect. Bit strange that it wasn't able to find an exact value without me doing a control enter, but sometimes the CAS does play a bit weirdly with weird functions. So that means we'll be taking this as our proper answer, but we'll be rounding it because it's said to round it to 2 decimal places, giving us final answer 6.71. So yeah, overall, the concept of finding area bound between two regions is based in integration. You just figure out what function's on top, what function's on bottom, and then how far does the area spread horizontally. You can either look at the picture that you've drawn or otherwise to determine how far it spreads, or you might be doing some solving to figure out where those endpoints are going to be. Part E, find the percentage error for the calculation of the area of the quarter circle. Okay, we've done a little bit of this before, percentage error. This is actually something you almost start looking at in kind of probability. It's similar concepts where you have areas of regions and you're comparing them to each other. Percentage error of the calculation for the calculation of the area of the quarter circle. So to give it a background on what's going on here, the true quarter circle equation is that square root one. It's that one in the dark red. And so if you were to find the area under the curve 0 to 10 for that red, the square root function, you would get the exact value of the area of the quarter circle. You would get exactly what you expect to be. Whereas if you used the, in this case, the teacher's attempt, which is obviously not going to be a perfect representation of the proper quarter circle, you get the blue dotted line. And if you were to do the area under that curve, it would be close, but not quite. Right? There would be this missing bit. And so when it says find the percentage error for the calculation, what it's essentially saying is, what's the percentage difference between if I were to do area of the red versus doing area of the blue? There's a couple ways you can go about this. I can give a hint saying that the previous answer will be helpful for this. Any ideas how I might go about doing this? Or even just like a step in the right direction? Which part are we looking at now? This will be 11D. Find area of the shaded region, correct to, E. Find percentage error. So we had just finished part D, finding the area of the shaded region, so the little bit between the red and the blue. That's what's on the calculator right now, the 6.7. That's the portion of area that's bound between those two. The next question is asking, effectively, what's the, if I were to find the area under the red and the area under the blue and compare them, what's the percentage difference between them? It's probably the easiest way to think about it. So with that in mind, how might we go about doing that?
They'd just be calculating the area of both the lower region and the upper region, and then just calculating the difference.
Yeah. So let's go ahead and do that then. So, area still going to be between 0 and 10. Let's do, I guess it doesn't matter which order we do it in. We'll know which one's which because we know which one's supposed to be bigger than the other. So we get our two areas, again using integrals. And when it comes to calculating our difference, how do you want to go about doing that specifically?
As in, like, the best way to find the difference? Or...
Well, we're trying to answer the percentage error, and this will help us get to percentage error. So, with this information that we now have, what do you think we should do with it?
And you could probably use answer and then just copy paste the first one and then minus it.
Oh, so just, yeah,
there's a better way.
subtract the two of them?
Yeah.
Yeah, sure.
Is there a better way, or?
Well, I'll maybe let you decide that based on what you're seeing on the CAS right now. We might notice something familiar. So the thing that I'm trying to point out here is that this so far has been a little bit redundant, because the previous question that we just did figured out the difference in raw numbers already.
Yeah.
We're still trying to find a percentage difference, which means we're not trying to do it in terms of the raw number anymore. We're trying to get it into a percentage of total. So when it comes to percentages, it has to be a percentage of total. That means we need to know what total actually is. So in the context of this question, you know, at least one of these is going to matter. One of these integrals was needed in the first place, so it's not fully wasted information.
Yeah, it'll be the outer one.
The outer one, yeah. The bigger area here, the one for the red. So
Yeah,
basically,
the value from D was the difference itself, because that was the area of the shaded region, which is the difference.
Yeah. And so from here, there's a couple of ways you can go about it. So you could do, probably the most direct way would be to have, okay, that one's the most recent, so if I just do that divided by this, and then I got to times 100 to get it to percentage. You could do it that way to get your percentage error, because it's how much is wrong, not how much is right. Alternatively, you could go about doing it the way you did, and rather than doing the subtraction, you just grab these two values, divide them through by each other, and you find, rather than the amount that's wrong, you find the amount that's right, and you say, okay, 1 minus that will get me whatever's wrong. And then again, just multiplying it up to get your percentage. You don't have to multiply it up on the CAS, you know, if you know that 0.0854 is 8.5-ish%, then don't worry, but this is just getting into its actual form.
Yeah, the other way is just a lot faster.
How much faster? Let's see. So, at bare minimum, we need this integral and the answer previous. So we do that, and then yeah, going with the by calculating the difference, you're getting there faster using the difference version as your numerator and then multiplying it through. You're skipping the 1 minus part. So yeah, I give both methods simply because well, there's multiple ways of doing it firstly, but it's good to explain the difference between what the question's actually asking. When it's saying find the error, you're saying what's wrong with it. If it's percentage of total, or you know how accurate was the drawing, maybe you would then have to say it's 91% accurate. So depending on how the question is phrased, you might want one or the other. So you now know how to do both if you need to. Cool. Okay. That's that. Part F. Teacher draws in a chord from 0 to 10, so just a straight line between the two intercepts. Find area of shaded region. Okay, maybe not. We've done that already. It's still just going to be a top take bottom. You would do the blue, which is the exponential. Take the red, which would be, well, I guess we could revise how to find the equation of a straight line. Or otherwise, actually, there's a couple ways you could do this. Let's maybe explore the other ways we could do this. So it's still going to be, you could do a top take bottom. Problem with that is you don't actually know the equation of the red line just yet. How would we find the equation of the red line, given that it's a linear straight line? quiet day today. No worries. Okay, so long as you know at least 2 points along a line, you can find the equation of that line. We have those 2 points. We have 0, 10, and we have 10, 0. And so all we would do is shove that into y cos mx plus c and simultaneous solve. You could shove it into the gradient point formula, and then it's just done. You just got to rearrange it from there. Either one would give you the equation, and then again, you just go to top, take bottom. That's pretty much it. The other benefit of having a straight line here is we can solve this question a little bit differently again. Let's say we're not allowed to, for whatever reason, we're not allowed to find the equation of this line. What's another way that we could get that bound area?
Find the area of the curve, then subtract the triangle area.
Yes, exactly. Finding the area of the curved bit, the blue dotted line, will give you the total bit. And because this red line's a straight line, it forms an implicit triangle. From y equals 10 to x equals 10, you just do half base times height. So half times the base of 10 times the height of 10 gives you the area of the triangle. So you get the bit here, subtracting the total, and what you're left with is the bit that was not overlapped. Which actually ends up being faster, because well, especially if you're doing it tech-free, half times 10 is pretty quick versus getting the equation of the linear, anti-diffing it up, and then doing a definite integral. So at least this way, you don't have to do one definite integral, and then the rest is... In fact, you don't even need to do a definite integral because you've already done it for part whatever in the previous part of question 11. So getting the area of the triangle will probably be the fastest approach there. Cool. GI looks fun. Okay, use the result that the derivative of the exponential is that to find 0 to 10 the integral by analytic techniques. So in other words, just algebra, basically. It's worded a bit fancily, but this is a question we've practiced many times before. I wonder if we can spot what kind of question this is. I'll even write it out in a specific way to hopefully spark an idea. Actually, maybe I'll get the brightness up a little bit. So we have d dx of e to the x on 10, 10 take x is equal to minus e to the x on 10 plus 1 on 10 e to the x on 10, 10 take x. And we want to use that information to find 0 to 10 of e to the x on 10. Oh, whoops, I don't know why I started writing that in green. Ex on 10, 10 take x dx. We want to use the information in green to help us with the information in red. This looks like a very similar question to what we've done before. Can anyone remind me of what kind of question this is and how we go about doing it?
Integration by recognition.
That's it, integration by recognition. So, you know, the wording in the question was, use the result that the derivative of this is that to find a related integral. As soon as you have derivative information and an integration that looks quite similar to some of those functions, you're doing integration by recognition. How do we do integration by recognition?
We can just make we can integrate both sides of the first function, the first equation.
Yep.
And yeah, we can separate the things, the terms.
That's it. Yeah. So
yeah, then,
integral of diff will cancel that out. Yep.
Yeah.
is equal to integral minus ex on 10 dx plus integral 1 on 10 ex on 10 x take 10 dx. Cool. Okay, we've integrated both sides.
We take the integral of negative e to the x over 10 to dx to the other side.
Yep.
And then we try and evaluate that.
Uh-huh.
Yeah, so oh yeah, and the 1 over 10, that too. We take for in the integral of e to the x over 10. We can do 10 e to the x over 10. Would that plus c? Would that be the...
Yeah, because it'll be
Yeah.
1 over rather... Actually, hang on, is exponentials different? I don't believe exponentials is different. Yeah. Let me just quickly double check. Integral e to the x on 10 dx. Yeah, no, exactly right. Dividing by 1 over 10 gets you a coefficient of 10. So yep, that'll now go to the 10e x on 10. Putting a plus c is... does it matter? We're going to be doing a definite integral anyway, but yeah, I guess putting a plus c in there doesn't hurt for now. Ex on 10, 10 take x.
We can simplify it by... We can simplify it to... wait... Okay, so we can take e to the x over 10 out. And
Yeah.
so that's going to be 10 minus x plus 10. So 20 minus x plus, e to the x over 10, yeah.
Yep, double
10
check.
plus 10, that's 20.
Yep.
Yeah. I can't really see how I can simplify it further. Isn't that the answer?
Well, it's not going to be our final answer because this is what we're
Oh
trying
yeah,
to solve.
it's 10. Yeah. So we have to use that 10. We have to shove in 10 and then subtract 0. X equals to 0.
It's a little bit premature. Have a look at what our
Oh wait,
right-hand
yeah,
side was.
there's a 1 over 10, so we can multiply the whole thing by 10.
Yeah.
I mean, yeah.
So to reiterate the goal here, basically by anti-diffing both sides, what we've done is we've tried to put something that looks like this into our equation. And this is the closest thing we have. It's the anti-diff of this function, very similar to this. Only difference is this one had a 1 on 10 in it, so we're doing our best to get that over to the other side, which would, I'll just put it down here at the very end. 10 times all of that is now equal to integral of e x on 10 x take 10 dx. And so if we compare this, integral ex on 10 x take 10, it's the exact same as this one. Ex on 10, 10 take x. Only difference being the terminals on this, which terminals just are basically another step afterwards. So we have the part that we needed, which was getting the general anti-diff. That's this bit. All we need to do now is complete the rest of the definite integral, which is a matter of... Remind me again, what do we do? You said it before.
What? Could you repeat that?
Yeah. So we've
The
now got
last.
our
I
general
didn't.
anti-diff.
Oh yeah. So we shove in the terminals.
Showing the terminals. Yep. So first part was getting our anti-diff. That's this bit. Second part is subbing the terminals. So if we call this thing capital F of x, this whole thing, then what we're doing is finding capital F of 10 minus capital F of 0. Just like with the bound area, you're always doing the top bit minus the bottom bit. Now, I did say do this analytically, so we are going to do this by hand, which shouldn't be too hard, I guess. So, we're going to have 10 E 10 on 10, because we're replacing x with 10. And there's 20 take 10 plus c. You know, I'll put it in here just so we can see once again that everything is going to cancel out. That right there is our f of 10. And we're going to minus our f of 0. So 10 bracket e to the 0 on 10. 20 minus 0 plus c. That there is our f of 0. Capital F of 10 minus capital F of 0. Now we... oh geez, did I just break? Okay, I got worried there for a second, I thought it just broke. Cool. Okay, now we're just going to simplify things. So, e to the 10 on 10 is the same thing as just e to the 1, which is just e. So, let's figure this out. 10 bracket e times 20 take 10, so 10. Plus the c, which I guess should be included in there. I'll start using different brackets because now it's getting a bit confusing. So we have 10 bracket e, because that's now just 1. And then 20 take 10 is 10 plus c. From here, e to the 0 is just 1. So we're now going to have 10 bracket 1 times 20 minus 0. So 1 times 20 just gives us 20. And there's still a plus c in there. From here, the rest becomes a bit easy. So e times 10 is 10, times another 10 gets you to 100. The c now goes up to 10c. And then minus 10 times 20, so minus 200, minus 10c. And that's pretty much it. You'll see the 10c and the minus 10c will cancel. These will always cancel, which is why we typically will ignore plus c in our indefinite integrals. Leaving you with final answer 100e minus 200. To be even better with your final answer, make sure you say that is equal to 0 to 10 e to the x on 10, 10 take x dx. Yeah, it's just a nice little way to say, hey, what I've written down here is my final answer, treat it as such. Okay, any clarification there? We've done a lot of these recently, but I know we also have a few new people arriving. Do we need to clarify any more of the procedure there? If not, have a read of part II. Okay. Part II. Find the exact area of the original shaded region and compare it to the answer of D. I don't really know what they're considering the original shaded area. It's indented into II, so... I mean, original shaded area would probably imply here, up until part D. But they're also saying compare it to part D. So I don't understand. So I guess what? Compare these two? Hang on, I'm gonna have to read this a bit more. Find exact area of original shaded. Oh, okay. So what? In part D, we got decimal places. In this case, it wants exact, and we're comparing it. Really? Find exact area of original shaded region and compare that to answer of D. Alright. I mean, original sounds to me like it's just question D, but instead of doing decimal places, we do exact. Well, we're going to see that it comes out to being... Maybe they meant to compare it to GI. Because at least that way you're integrating. Well, no, because you're still... Because what we just did there was the tech-free way of finding the area underneath this blue dotted line. If we look back at the screen share. 0 to 10 of that function, it's the same function we started with. So we're finding the area under the blue. That's what this has told us to do. Now, this being a follow-up, you know, we're not going to have this answer show up here because that's way too big. It's trying to compare to this. Shaded regions are only this small little sliver. So it's not asking about that. If I had... Whoop, did I just crash? Can people still hear me? I think my camera turned off for some reason. Okay.
We can still hear you. I think it's just the camera.
Yeah, okay, that's... Let me see if I can plug that in again real quick. If not, I guess we'll just go without my face. I guess you don't really need to see me, do you? Cool. Okay, so if I had this in the SAC, I think... Geez, what would I even do? What are you supposed to do here? You can't really compare... I guess let's just do it anyway. So if we just scroll all the way back up to what we did for part D, so we're looking for two functions integrated. That's this one. So here's our exact. And we're comparing that to decimal. So we're just comparing these two things. Yeah, I don't know what this is asking. Let me check the answers. Okay. Okay. The word compare was completely ignored apparently. The answer to path double I is to say the exact area of the shaded region is that. Great. Awesome. Sure, why not? So that was a bit of a weird wording there. Let's just pretend that question didn't exist. That's a really bad one. Okay, I'm about to get time here. Maybe what I'll do is I'll introduce what's coming up next, and then we'll talk about it next time in the next Friday. So we got some exponential combined with a circular function. So far, part AI and AII is just shoving in values, right? This is our R of t, so R of 0 just means replace t with 0, R of 3 just means replace t with 3. That's pretty quick. You can cas that out really easy. Find R dash, again, for those who aren't too familiar with derivatives, this is another way of representing derivative. You don't just have to do dy dx, you could have f dash or R dash in this case. And this is again one thing you can cas solve, or if it was tech free, you would do product rule, because you have an exponential multiplied by a circular function. Those are two separate functions. You now want to, that's where the product rule comes into play. This is again immediately just cas solvable. You now have your derivative at this point, so you would just literally cas solve derivative equals 0 and chuck in your domain as we've seen before. Find coordinates of the stationary points. You would just again use that derivative and set it equal to... Never mind, we've already done that. So you've already got the x coordinates of your stationary points at this point. That's what part I has given you, derivative equals 0. And so to get the remaining set of coordinates, because you only have the x portion of those, you're just going to take those x values, shove them back into the original function, not the derivative, but the original, to get the corresponding y. because this is a function that has both y and x values. Derivative only has gradient and x values. Solve and sketch. I mean, again, this is just the same question as this basically, but using the original. Sketch, you got the cas, so just use the cas. And the rest of these have got to do with, again, derivatives. Or, well, actually maybe not. But yeah, not quite enough time to cover the rest of that. So a decent amount of this is some basic stuff. Even in the actual exam, you'll find that a decent amount of beginning questions are basic enough to at least get you started. So it's not too weird to have that. Like even if you compare here, right? Find derivative, find gradient, area of a bound area. Like these are things that should be, at least by the time you get into your SAC or exam, quick fire, easy questions for you to do. If you're not there yet, that's fine. Just know that this is the sort of stuff that you need to be able to quick fire do. Alright, that's about it. Bit of a shame the camera died right at the end, but either way. If there's any further clarifications or anything that I need to explain further, feel free to stick behind and ask me, and I'll do my best to explain. Otherwise, thank you so much for coming.
Thank you so much. Have a good day.
Yeah, no problem. Thank you.
Okay, thanks. Have a good day.
Thanks.
Hey Chris, I was wondering, like for the this thing now is a Chapter 11 extended response, right?
Yeah, that's right.
Okay, so when did what was the first session we started working on this? Because I just wanted to go back to the recording.
First session we did extended responses for the Chapter 11. Good question. It'll be fairly obvious in the first couple of seconds of the video.
Yeah, I'll have
and
to.
yeah, it's got to be. Yeah, it'll be okay. It'll be either.
But it'll probably. I'll just have to check through the Tuesday and the Friday.
Yeah, the Tuesday, Fridays. Let me. I can even just try to look for it now, I guess. They're all posted at this point. It was a relatively recent thing. I think I even started mentioning we were doing chapter review stuff in the actual descriptions of them, so maybe that can also help refine our search a little bit. So I'm going to have a look through class 2 right now. We'll see when I started mentioning that. Okay. Focusing integration, Cambridge chapter review. Okay, cool. Maybe it was term 2, week 10. Let me have a look. Okay, maybe not quite actually. I think I mislabeled that one. So term 2, week 10, class 2. Maybe it was a class 3 one. So term 2, week 10. Yeah, so term 2, week 10, class 3.
So term 2, week 10, class 3.
That looks about right. We're looking right at the start of the extended response section. I did answer some student questions in there regarding circular functions, but we did look at
Awesome. Thanks, Chris.
oh yeah, no worries. Sorry, I was listening to the video. It's hard to hear.
Oh, no, that's so good. Yeah, no, I just wanted to check because yeah, I just wanted to go back through it.
Yeah.
Just to
Yeah.
make sure.
Like I think it's near the latter part where we start looking at the exact first question, because it was, yeah, we looked at some circular function stuff there for the review. But yeah, near the latter half of that video, we start with that extended response bit.
Awesome.
Cool. Yeah, keep me in the loop should you need anything else.
Will do. Thanks, Chris. Have a good night.
Thank you. You too.